I'm Michael Fausnaugh, a graduate student at The Ohio State University. In this video, I will discuss my recent paper, A New Approach to the Internal Calibration of Reverberation Mapping Spectra. Reverberation mapping is a very successful way of exploring the spatially unresolved structures around supermassive black holes and active galactic nuclei, or AGN. The basic principle is to search for strong variable emission signals and their corresponding light echoes, which are caused by reflection or reprocessing from matter surrounding the central black hole. Using light travel time arguments, the time delay between the signal and its echo provides a measure of the characteristic size of structures in the AGN. Reverberation mapping has become a well-calibrated means of measuring supermassive black hole masses, and these mass measurements in turn calibrate the scaling relations used to infer the majority of black hole masses in the universe. In order to measure the time delay of light echoes, it is necessary to measure the intrinsic flux variations of the AGN. This requires some treatment of extrinsic variations, such as those caused by changing observing conditions from night to night. For example, the presence of clouds can introduce variable amounts of attenuation in the observations. Other variations can be introduced by shifts in the wavelength calibration or changes in the spectral resolution, caused by variable seeing and spectrograph focus, or flexure in the telescope and optics system. The usual approach is to model and remove extrinsic variations on the assumption that narrow emission lines in the AGN spectra are constant over the course of the monitoring campaign. Oxygen 3 at 5007 angstroms is an ideal choice for low redshift optical campaigns, since this line is very strong and relatively unblended with other spectral features. The most popular calibration procedure was developed by Van Groningen and Wanders 1992, which I will refer to as GW92 for the remainder of this video. Their model corrects extrinsic variations using a wavelength shift, flux rescaling factor, and smoothing kernel. The wavelength shift corrects for errors in the wavelength calibration, the flux rescaling factor for differences in attenuation, and the smoothing kernel for differences in spectral resolution. The approach presented in this paper improves on the GW92 formalism in several ways. In particular, it defines a single and consistent resolution for the final calibrated spectra and employs a more flexible model for changes in the spectral resolution. We have developed a Python package called MapSpec to implement the new approach, and in a test case, we have found that the MapSpec procedure reaches precisions of 0.1%. The test case is new optical monitoring data of the Seyfert-1 galaxy MCG 081111 from observations taken in 2014 with the 1.3 McGraw-Hill telescope at MDM Observatory. MCG 081111 is a low redshift object and displays strong variability signals over the course of the campaign. In this figure, we show light curves extracted from the time series spectra. The continuum at 5100 angstroms is in the top panel, broad H-beta emission is in the middle panel, and narrow oxygen 3 5007 angstrom emission is in the lower panel. For the continuum and H-beta light curves, it is clear that the choice of calibration makes little difference for the overall structure. However, the MapSpec calibration greatly reduces the amount of scatter in the oxygen 3 light curve, which can be interpreted as an estimate of the calibration precision. There's a factor of 5 improvement over the GW92 calibration, resulting in a precision of about 1 millimagnitude. For other objects, the GW92 approach results in calibrations precise to only 3 or 5%, in which case a factor of 5 improvement is very meaningful. Further investigation also shows that the noise in the GW92 oxygen light curve propagates to continuum and line light curves. The MapSpec Python package is freely available and can be downloaded from GitHub. The code is object-oriented in order to facilitate modularity and extensibility. It also includes useful data structures for organizing spectroscopic data with emission lines, including analysis tools for interpolation, rebinning, line extraction or integration, and model fitting. A more detailed description of the method, as well as additional results related to the improved calibration, can be found in the paper. Thank you for watching.